How would you travel to another star system? Space is big. You just won't believe how vastly, hugely, mind-bogglingly big it is. Douglas Adams wrote that in 1979 as a joke. It was not a joke. The nearest star to our sun is Proxima Centauri. It sits 4.37 light-years from Earth. Light travels at 299,792 kilometers per second. It takes light 8 minutes and 20 seconds to reach Earth from the sun. It takes light 4 years, 4 months, and approximately 18 days to reach Proxima Centauri from here. Voyager 1 has been traveling since September 5, 1977. As of 2026, it has covered approximately 172 astronomical units. Proxima Centauri is 268,000 astronomical units away. Voyager 1 has covered roughly 0.06% of the distance. In 48 years of continuous travel at the fastest speed humanity has ever achieved for a departing spacecraft, at Voyager's current velocity of 17 kilometers per second, reaching Proxima Centauri would take approximately 73,000 years. If it were pointed that direction, it is not. So the question is not whether we can travel to another star system, the question is what it would actually take. And the answer is not what most people expect, because the speed problem, it turns out, was never the hardest part. Start with the thing everyone focuses on: speed. To reach Proxima Centauri in a human lifetime, say 80 years of ship time, you need to travel at roughly 5% of the speed of light, 15,000 kilometers per second. That is 882 times faster than Voyager 1. It sounds impossible. In terms of pure physics, it is not. Several propulsion concepts, theoretically grounded, none currently buildable, could get you there. The question is, which one comes closest to reality? The first serious candidate is nuclear pulse propulsion. Project Orion, studied by NASA and the US Air Force from 1958 to 1963, proposed detonating a continuous series of nuclear bombs behind a heavily shielded spacecraft. The detonations pushed the ship forward. The physics is clean. A large Orion-class spacecraft using thermonuclear devices could theoretically reach 3 to 5% of the speed of light, precisely the range needed for a human lifetime voyage to Proxima Centauri. The project was canceled under the 1963 Partial Nuclear Test Ban Treaty, which prohibited nuclear detonations in space, not because it would not work, because the politics made it impossible. But that is not the most promising option on the table right now. That distinction belongs to something far smaller and far stranger. In April 2016, a project called Breakthrough Starshot announced a plan to send a spacecraft to Alpha Centauri in approximately 20 years. The spacecraft would weigh roughly 1 gram, about the mass of a paperclip, and it would be pushed to 20% of the speed of light in under 10 minutes. The mechanism is a light sail, a sheet of material, target dimensions of 4 meters by 4 meters, target weight of 1 gram, launched into orbit and then struck by a ground-based laser array, producing 100 gigawatts of power. The photons hitting the sail apply pressure. Enough pressure, applied for roughly 9 minutes, accelerates the sail to 20% of the speed of light. At that velocity, the trip to Proxima Centauri takes approximately 20 years. The project was announced by investor Yuri Milner, with backing from Stephen Hawking and Mark Zuckerberg. $100 million committed to proof-of-concept research. 37 research groups convened worldwide. The physics was confirmed. The concept was sound. By 2025, the project had gone quiet. Scientific American reported what it called the quiet demise of Breakthrough Starshot. The research had revealed the full list of problems that needed solving, and the speed problem, it turned out, was manageable. Everything else was not. Yet. Here is what the engineers found when they started working through the actual requirements. The sail needs to be 4 meters wide and weigh 1 gram, stretched across 16 square meters, thinner than a human hair across its entire surface. And it needs to survive being struck by 100 gigawatts of laser power, an acceleration of 40,000 times the gravitational force of Earth, without tearing, melting, or deforming. The leading material candidate as of the 2024 research summary is silicon nitride. It has not been fabricated at anything close to this scale. The 100 gigawatt laser array needs to be coherently focused on a 4-meter sail from the ground, tracking a moving target in orbit, maintaining accuracy to within centimeters across tens of thousands of kilometers. The optical aperture required spans approximately 3 kilometers in diameter. Nothing of remotely comparable scale exists. At 20% of the speed of light, a grain of interstellar dust, a particle 1/10 of a millimeter across, hits with the energy of a rifle bullet. The interstellar medium is not empty. It contains dust, gas, and particles at densities that have not been fully mapped. A 4-meter sail traveling at 60,000 kilometers per second cannot steer around anything. And then there is the communication problem. At 4.37 light-years distance, any signal the craft sends back takes 4.37 years to arrive. A 1-gram spacecraft operating on solar power from a red dwarf star 880,000 times dimmer than our Sun. The estimated data rate back to Earth, between 2 and 15 bits per second. Not kilobits, bits. Slower than a 1960s telegraph. None of these are physically impossible problems. Every one is an engineering challenge rather than a violation of known physics. But the gap between current engineering and the engineering required is not small. It is generational. And that gap changes everything about the answer to the question, because there is a deeper problem that nobody talks about. This is the part that reframes the entire conversation. Everything above, the light sail, the laser array, the dust problem, the communication problem, is about sending a gram of electronics to another star, not a human being, a paperclip with cameras. The speed problem for a paperclip is theoretically manageable. The speed problem for a crewed spacecraft is a completely different problem. And the bottleneck is not propulsion. The bottleneck is mass. To accelerate a crewed spacecraft of 100 metric tons to 5% of the speed of light using nuclear fusion propulsion, the fuel mass ratio, the ratio of fuel to total ship weight, needs to be somewhere between 1,000 and 1 million, depending on the propulsion method and whether you need to decelerate at the destination. A ship weighing 100 tons at arrival needs to leave Earth with between 100,000 and 100 million tons of fuel. At the lower end of that range, that is the mass of a small mountain, being converted to thrust, continuously, for decades. That is not the reframe. Here is the reframe. A physicist named Robert Forward, one of the most serious interstellar travel researchers of the 20th century, argued that any interstellar mission that cannot be completed within 50 years should not be started at all. His reasoning: the propulsion technology available when the ship arrives at its destination will be vastly superior to the technology used to launch it. A ship sent today at 5% of light speed, arriving in 80 years, might be overtaken en route by a ship launched in 50 years using technology not yet invented, traveling at 20% of light speed and arriving first. The most rational response to the interstellar travel problem may be to wait, not forever, but until the propulsion technology has advanced enough that the journey time falls below the threshold where it makes sense to go. That threshold, according to most serious researchers, is somewhere between 20 and 50 years of ship time. Assume we solve all of it: propulsion, materials, mass ratios, solved. A crew is now traveling to Proxima Centauri at 10% of the speed of light, a 43-year one-way trip. What happens to the people? At 10% of light speed, relativistic time dilation is real but modest. The crew ages approximately 0.5% slower than people on Earth, a difference of about 77 days over a 43-year journey. Not the dramatic time jumps of science fiction, not biologically significant. What is biologically significant is the radiation. The interstellar medium is permeated by cosmic rays, high-energy particles traveling at near-light speeds, originating from supernovae across the galaxy. On Earth, the atmosphere and magnetic field absorb almost all of it. In deep space, there is no atmosphere. There is no planetary magnetic field. The shielding required to protect a crew from decades of cosmic ray exposure is heavy. Heavy shielding means more mass. More mass means more fuel. More fuel means more mass at launch. The engineering spiral compounds. Then there is the psychology. No human being has spent more than 437 consecutive days in space, the longest verified mission on record. The International Space Station provides regular resupply, communication with minimal delay, and the constant psychological anchor of knowing rescue is hours away. A crew bound for Proxima Centauri would be unreachable. Communication delays of years. No resupply, no rescue, no return. Not within any human lifetime at currently plausible speeds. Hibernation is sometimes proposed as the solution. Induced metabolic slowdown. It has been demonstrated in small mammals. It has never been demonstrated in humans at the scale of years or decades. The fundamental biology, whether the human brain and cardiovascular system can tolerate that duration and return to full function, is genuinely unknown. Not unsolved, unknown. The experiments have not been run. So what is the actual answer? How would you travel to another star system? The honest answer in 2026 is this. You send a probe first. A gram of electronics on a light sail, pushed by a laser array that does not yet exist, made of a material not yet fabricated at scale, surviving a dust environment not yet fully mapped, transmitting data back at telegraph speed. That probe arrives in approximately 20 years after launch, if every engineering problem is solved. It spends about 2 hours in the vicinity of Proxima Centauri before flying past at 20% of the speed of light. There is no way to slow it down without carrying fuel. Carrying fuel makes the concept physically impossible. The images it sends back take 4.37 years to arrive. By the time the first frame reaches Earth, the probe is long past the system and still moving. That is the most optimistic, realistic scenario currently supported by physics and engineering. Not a generation ship, not a warp drive, a paperclip flying past a star and transmitting blurry images at telegraph speed. But here is what makes that answer feel different from impossible. Every technology in the breakthrough starshot concept is an extension of something that already exists. Light sails have been demonstrated in orbit. LightSail 2, launched in 2019 and built on Carl Sagan's original concept, successfully raised its orbital path using only sunlight pressure. Phased laser arrays exist at lower power levels and are being developed. Silicon nitride films exist at small scales. The problems are engineering problems, not physics problems. The gap between where interstellar travel is today and where it needs to be is not a gap in our understanding of the universe. It is a gap in manufacturing capability, materials science, and energy production. Every one of those gaps has been closing continuously for the last 100 years. In 1903, the Wright brothers flew at Kitty Hawk. 66 years later, humans walked on the moon. The gap between a 12-second powered flight and a 384,400-kilometer journey was closed in one human lifetime. The gap between Voyager 1 and Breakthrough Starshot is roughly 1,000 times in velocity. The gap between Breakthrough Starshot and a crewed interstellar mission is perhaps 100 times more. Both gaps are large. Neither is physically prohibited. The question is not whether humanity will reach another star system. The question is how many generations it takes, and whether the first step, the paperclip with cameras, happens within the lifetimes of people currently alive. The technology gaps are real, the funding has stalled, but the physics is clean, and physics has never been the limiting factor in human exploration. The limiting factor has always been will, money, and time. Douglas Adams was right. Space is big in a way that resists comprehension. Proxima Centauri is the nearest thing to us outside our own solar system, and it is so far away that Voyager 1, launched 48 years ago and still operational, has covered less than 0.1% of the distance. By the time it reaches the vicinity of any other star, everyone alive today will have been dead for 40,000 years. And yet, the paperclip is real. The physics is real. The 20-year journey is real in theory, waiting on materials, lasers, money, and will. The first image of another solar system, taken by something we built and launched and aimed, is not a fantasy. It is an engineering project with a checklist. Think about where you are sitting. The star you orbit is one of approximately 200 billion in this galaxy alone. Proxima Centauri, the nearest of those 200 billion, is close enough that light from it reaches your eye in just over 4 years. Every other star you see with the naked eye is further. Most of them are hundreds of light years away. The galaxy is 100,000 light years across. We are attempting right now, in the earliest infancy of our technological civilization, to bridge the gap to the closest star. Not with a warp drive, not with science fiction, with a gram of electronics, a laser, and a sail thinner than a human hair. The universe was here for 13.8 billion years before we arrived. It will be here long after we solve this. But the fact that we are trying, that we are sitting on a pale blue dot, calculating trajectories to other suns with the same physics we use to put footprints on the moon. That might be the most extraordinary thing about this particular moment in the entire history of the cosmos.